All right, so next we see measures of variation. So in a given data set, you can calculate the averages for that data set, but you are also concerned with the variation in the data set, that how uh, data varies in, in reference to different elements or subjects. For example, when we talk about age and we have selected the data from multiple colonies, we would like to see that which colony has more variation, where more diverse kind of people are there in respect to the age of people. So when we talk about variation, we can have a few values that can indicate the variation. One very raw value is a range. And number two, we can have variance, okay, which is basically a squared average deviation within the data set. And then we have a standard form of variation, which is called standard deviation. Okay, and then we have coefficient of variation. So these are different types of variations that we can measure. There are other forms of variation. For example, you can also calculate the covariance or the correlation of the data points, but that is, that is included in the further topics. Okay, first of all, we're going to see range. When we look at a data set, the range is basically the difference between the maximum value and the minimum value. In this particular data set, you can see that the highest value is 67 and the lowest value is 56. So range is the spread of data. Spread of data means where the data starts and where the data ends. The maximum value and the minimum value, these are the 2 points that actually indicate the spread of data set. So when we look at two raw data sets, the very first thing that you can easily identify is the spread between those data sets. So range is a very raw kind of indication towards the spread. Next, we talk about deviation. Now, the very basic form of variation in data sets is the variation of a particular data value from the center of the data. Remember, in the calculation of different kinds of central tendency measures, we saw that we calculate mean, median, or mode. So what if I calculate a mean of a data set, and then I see that how each data entry of a data set falls away from the mean, how much distance is there between the data entry and the mean. The same is going on here. For example, the mean here for this data set is 61. How did we calculate that? Remember, mu is equal to summation x over n. So we added up all the values and the product was 305. And since there are only 5 values, we divide that with 5 and we get 61. So this is the mean. 61 is the mean. Next, we're going to see the deviation. So for finding out the deviation, we just deduct a value from the mean. So we deduct different values from mean. For example, 56 minus the mean is minus 5. 58 minus 61 is equal to minus 3. 61 minus 61 is equal to 0. 63 minus 61 is equal to 2, and 67 minus 61 is equal to 6. Okay. So now here you can see that there are some negative variations and there are some positive variations. Now let me draw a line here. And mean is exactly in the center of the data, right? So we have a few data values that are lower than the mean and some data values that are higher than the mean. And if we calculate the distance from the mean towards these values, you will find out the distance to all the values to the left and right would be canceling out each other, because mean is in the center, exactly in the center. So that central tendency of the mean actually helps us understand why there are equal amount of negative as well as positive variations. So you can see there are positive 8 points of variation and negative 8 points of variation. And when we sum up the variation or deviations, we get 0, which is not so meaningful. So this is a problem in statistics when we actually compare the data points with the mean. the deviations that we calculate, they in total become 0 because you have similar deviations to the left and the right of the mean. And why is that? Because mean is the central tendency, it's in the center. Okay, so avoiding that particular flaw that we saw in the total of deviation, what we do, we actually square up every deviation. Here you can see the formula of variance, that sigma square, this is sigma square, is equal to summation of x minus mu. X is the individual data entry, whereas mu is the mean of the data. Since the sum of all these values is 0, what we do, we actually square these deviations. And you remember that when you square the negative values, they also become positive. So the result won't be 0 this time. We will see for that. And then we have a capital N down in the denominator. And one more point to understand here, we are talking about population variance. Again, we denote the population variance by sigma. And when we talk about sample variance can be denoted by S square. And that is equal to x minus x bar. Remember, x bar is the mean for a sample squared divided by small n, because sample size is denoted by small n. And what if I want to calculate standard deviation? I only have to take the under root of variance. And why we take under root of the variance? Just to cancel out that squaring effect that we implemented in order to avoid that 0 situation. So here are the guidelines, and these are very important because later on in your subsequent chapters, you will see there are concepts that relate to these points. So let's be very thorough about these. First of all, find the mean of the population data set. And this applies to a sample as well. If you want to calculate the sample standard deviation, the procedure is very similar. So first of all, we find the mean, and there is formula of the mean, mu is equal to summation x over n. Then we find the deviation of each entry in the data set. So every x is subtracted from the mu, the average of the data set. Then we square that deviation. Each deviation is squared. And when we total up those squared deviations, we call it sum of squares. So this is a concept which is used in ANOVA and regression also. So this is a very important concept, sum of squares, because we are summing up the deviations here. And then we divide by n to get the population variance. So when you have summed up deviations that are called sum of squares, you divide the sum of squares with population size, okay, n. And dividing by n, we get population variance. And if you take an under root of this whole product, you get standard deviation, right? Now we have to get the under root to make it meaningful. We will see that through the example of standard deviation. And here is a calculation for sample standard deviation. The only difference that you see in the sample standard deviation is the denominator, where in place of n, you're using n minus 1. Again, you calculate the mean, you deduct each entry from the mean, and that gives you the deviation. You square each deviation, then you find out the sum of squares by summing up all the squared deviations, and then you divide that sum of squares by the sample size minus 1. Why minus 1? Now, this concept is a little thorough concept, and this is not included in the scope of basic level statistical courses. But let me give you a little hint about this. For example, when you calculate the total variation in a population is a larger set of elements. But when you calculate the total variation of sample, that is not completely representative of the population, because sample is only the subset of the population. So your calculation is biased. Why it is biased? Because it is based upon on a few elements. So actually, to enlarge enough that variation that you're finding, what we do, we deduct minus 1 from the sample size. Why minus 1? Well, statisticians have tried many numbers, but this seems to be the only one that actually keeps these two values very close, the sample standard deviation and the population standard deviation. So whenever you calculate the standard deviation for sample, what you got to do, you have to deduct and -1, you have to do that. So your formula is right. Okay, here's an example. Again, you have these values, x values, x1, x2, and then x3, x4, x5, and you detect these values from mean, and you get these deviations. The total of deviations is of course 0, but to avoid that, you sum them up. So -5 squared is equal to 25, -3 squared is equal to 9, 0 squared is equal to 0, and 2 squared is equal to 4, 6 squared is equal to 36. And when you total them up, sum them up, that is 74. And since this is a population parameter, so we are dividing with capital N, that is 5, and we have a variance of 14.8. Now this 14.8 is not that meaningful for us. Why? Because we have squared effect here. We have squared all these deviations. So our variation that we are seeing in the form of variance is kind of squared. So to reduce that effect, we take a square root of this, and the answer is 3.85. So this is a meaningful answer. So the average variation in the data set, the standard average variation in the data set is basically 3.85. So if we have a mean of 61 and we have a standard deviation of 3.85 in research, usually you will see that research papers or research scholars, they try to write it down like x bar plus minus s, or mu plus minus sigma, and here that can be written as 61 plus minus 3.85. Now if you ask me why plus minus, why plus and minus both, because whenever you take the under root of a product, the answer is also in the form of plus as well as in negative. Now let's interpret the standard deviation. What is standard deviation, and when we find out the standard deviation of a data set, what does this indicates? Here you can see there are two histograms. That means we are showing two data sets here, and we have only one bar in the B data set, but there are multiple bars in A data set. So A data set has more spread in it. That means the deviation or the variation in the data is a lot more than the B data set. So you can see that it has no variation, it has no standard deviation. But since A dataset has 1.18 points in standard deviation, that means there is a lot of spread, a lot of variation as compared to B. Okay, so if you look at the mean of these two datasets, they are same. So sometimes only looking at the mean or average of a dataset can be misleading. So you have to look at two things. First, where is the center of the data, and then how much variation is there in the data. If you look at these two data sets, you can see that the center of the data is exactly at the same point, but they are different from each other in respect to their variation.